So in the same Dirac potential problem, we are going to see about scattering states. The scattering state we said is for energy greater than 0. So we'll see in the two regions where x is less than 0 and x is greater than 0. So x is less than 0, x is greater than 0. So in the region x is less than 0, we have these set of solutions, and in the region x is greater than 0, we have these set of solutions. Now by we said that psi should be continuous. The function psi about the distribution function should be continuous, right? It is one of the boundary conditions that we spoke about. So it requires that it is continuous. So at the origin, so when we solve for that, we get the relation between the constants f plus d is equal to a plus b. And the second condition was that the derivatives are discontinuous at the origin by some amount. Okay, so we take the derivatives of these two solutions and we take the difference in the derivatives. So that will tell you, so the difference in the derivatives given here, that will tell you how much it is discontinuous, by how much the derivative is discontinuous by. Now we can use these set of equations now, and meanwhile for x is equal to phi is equal to 0, we have this set of values, so initial conditions. So now we can use these set of equations and we can, so in the bound state lecture we had derived a value for del d psi by dx. Okay, that was this value, and this a plus b was actually psi naught. Okay, psi at the value 0. So that we are equating to this value that we found here. So we are equating that, and we write it more compactly by using the definition for beta. Okay, we define this beta to be this quantity, and we rewrite this more compactly. Now let's see the physical meaning of these constants here. So A is the incoming amplitude and B is the reflected amplitude. F is the transmitted amplitude and G will be scattering from the left, but it will be 0, right? Because the incoming amplitude is, the incoming wave is from the left, so it can't, so G will necessarily be 0. So using all these relations, we write B in terms of A and F in terms of A, and now the ratio of these constants. So if you take the ratio of the B by A, what you would get is the reflection coefficient. So how much it is, so A tells you how much incoming, B tells you how much it is reflected, so it will tell you the reflection coefficient. Similarly, F by A will tell you the transmission coefficient, so how much it is coming in and how much is transmitted. Okay, so it will give you the transmission coefficient. So the reflection and transmission coefficient are given here. So we take the, for amplitudes we take the square so that we don't get any negative values. And then we have, so if you add up R and T, you should get 1, because what is coming in should, here there is a conservation that what comes in should go out, right? So transmission and reflection should add up to 1, so that adds up to 1. You can check that out. So these are the equations. So just substitute the value for beta here, and that is the R and T, reflection and transmission coefficient, are written in terms of energy, mass of the particle, and height of the potential, Dirac delta potential.